Hello, everyone. My name is Jun Zhang from Nanyang Technological University, Singapore. Today, I'm going to talk about our work on 3D radar and thermal camera calibration. In this work, we proposed a new calibration target. It's called a Spherical-Trihedral. This work is sponsored by NTU, A-STAR, and the National Robotics Program, Singapore. This is the contents of today's talk. There are 5 parts: introduction, literature review, methodology, experiments, conclusion, and future work. First part is the introduction. The motivation of this work is to achieve robust perception in adverse environments, such as rain, snow, smoke, and fog environments. As shown in this video, we can see that in the smoky environment, the visual camera and the 3D LiDAR cannot work very well, as we can see here. But the thermal camera can work well and can detect human beings behind the smoke. As shown in these images, we can see the same results. So we want how to achieve the robust perception in this environment. In this work, we can fuse the 3D radar and the thermal camera. So first, our objective is to do the extrinsic calibration between the 3D radar and the thermal camera. The 3D radar is shown here. It's Ocu9 Eco. It can provide XYZ and the velocity information. For the thermal camera, it is shown here. The challenges of this calibration is the suitable target design to achieve common feature extraction between the 2 sensors. So in the second part, it's the literature review. As shown here, we can see that a lot of work are proposed to achieve the calibration between 2D radar and the RGB camera, but it cannot work well with the 3D radar. Recently, a work is proposed by WISE in ICRA 2021 to achieve the calibration between a 3D radar and the RGB camera. But for those works focused on 2D radar, some of them require to manually select the target and to extract the features. Some of them require a medium sensor to assist the calibration so that the calibration error will be increased. And some of them extract the feature or detect the feature indirectly. And some of these works require the motion of the sensors to do hand-eye calibration, which is not suitable for the V2X environment. So in this work, we proposed the 3D radar to thermal camera calibration, and it can achieve the calibration between a 3D radar and a thermal camera. And also, we don't need to move the sensors. The third part is the methodology. Firstly, we propose this new target, a Spherical-Trihedral, as shown in this image. This is made by 3D printer. First is a sphere, and within the sphere, there is a trihedral inside this sphere. And we stickered the tin foils on these 3 faces of this trihedral. To do the calibration, we need to put the target in front of the 2 sensors, as shown here. By putting the target at different positions, different height, and different distance, we can extract the sphere center from each sensors, as shown here. Then put the target at a further distance and extract the sphere center from 2 sensors. Then, by minimizing the 2D reprojection error, we can obtain the optimal rotation and translation parameters. This shows the flow chart of the whole pipeline. There are 3 parts. For part A is to extract the sphere center in the thermal image. It's 2D sphere centers, the output. In part B is to extract the sphere center in the radar. The output is a 3D sphere center point. And in part C is to do the parameter regression. The basic idea is to minimize the reprojection error, and the optimal rotation and translation can be obtained. Next, I will introduce each module in details one by one. First is the part A. As we can see, the input is a raw thermal image, and the target is heated up. First, we do the undistortion, then do the binarization of this image. Then we will find the contour of this target, as shown in this red circle. After that, we will extract the minimum enclosing rectangle of this contour. Then the center point of this rectangle is used as the sphere center. After that, we will accumulate multiple frames and calculate the centroid as shown in this green point. Then this is the 2D sphere center extracted from the thermal image. In part B, the input is the raw point cloud. First, we will do the target segmentation as shown in this blue circle. Then we will detect the target based on the intensity values, because the target always returns higher intensities. Then we will accumulate multiple frames and calculate the centroid. The final sphere center is shown in the red color. After that, we will put the sphere target, Spherical-Trihedral target at several different positions to collect a bunch of data. As shown here, this is the sphere centers detected from the radar, several sphere centers. And this is the several sphere centers detected from the thermal camera. By minimizing the 2D reprojection error, we can obtain the optimal transformation matrix. In the thermal camera, to detect the sphere center, why do we need the minimum enclosing rectangle? It's shown here. Because our target is not a perfect circle, so the RANSAC cannot work well in our case. And we found that the minimum enclosing rectangle is a good way to extract the center point. From the radar, why can we use the intensity to detect the sphere center? That's because before and after the target is put in, the intensity distribution is different. The left column shows the image and the intensity distribution between the target is put in. We can see that all of the points, the intensity are lower than 25. From the right column, we can see that after the target is put in, the intensity is different. Some of the points, the intensity is larger than 25, so that we can use this property to extract the sphere center from the radar. Then comes to the experiments. Here shows the quantitative analysis. Because in the real environment, we cannot obtain the ground truth values of the extrinsic parameter. So we use this reprojection error of the sphere centers to evaluate the calibration accuracy. The reprojection error is calculated in this equation. And as we can see that by putting the sphere at 40 positions, the reprojection error starts to converge. And the final reprojection error is about 1.9 pixels. And in this one, we show the sphere centers detected from the radar, the sphere centers detected from the thermal image. By reproject the sphere center from the radar to the thermal image, we can get this image. As shown here, the green points is PTI. It's the sphere centers detected from the thermal image. The PRI hat, the purple one, is the projected sphere centers extracted from the radar and projected onto the thermal image. Then we can calculate the reprojection error, and the result is plotted in this table. We can see that the final reprojection error can approach 1.88 pixels. In this video, it's a quantitative analysis of the projection results. It's in the indoor office environment. As shown here, the human is holding the target and in front of the sensors. The right point cloud shows the point cloud from the radar. And this image shows the projected points onto the thermal image. The blue color means the points are with higher intensity. That's the target. The green points means the higher velocity. That's because the human is moving. So we can see that the projected points overlap quite well with the thermal image. That means the calibration is accurate. In this experiment, we do the evaluation in a basement car park, and the human is standing much farther away. It's about 20 meters away. And we also project the points from the radar onto the thermal image. As we can see that while the human is moving, the blue and the green points will move as well. In this experiment, we evaluate the performance in an outdoor car park. The human is holding the target, and as we can see, blue points means the points are with higher intensity, that's the target. Green points means the points are with higher velocity, and the white points means the points with zero velocity and lower intensity. We can see that the projected points overlap quite well with the human being. And in this is in the same environment, but the human is standing far away, about 10 meters to 20 meters, and the human is walking from the left to the right and from the right to the left. From the zoom in part, we can see that the green points and blue points overlaps quite well with the human being. Finally, comes to the conclusion and the future work. To summarize, in this work, we proposed 3DRadar2 calibration to achieve the extrinsic calibration between a thermal camera and a 3D radar. Second, we proposed a new target. It's a spherical-trihedral. It's made by 3D printing and it's easy to be manufactured. Third, we achieved a reprojection error of 1.88 pixels, and it's quite accurate, as shown in this image. For future work, we will try to apply the calibration results to adverse environments, such as object detection and the SLAM exotic. Second, we will try to do the online calibration. That means without this special calibration target, how to do the calibration. And that's all for my presentation. Our paper ID is 897. If you are interested, please get more details with our paper. Thank you all for your watching.